and answer. I think it's number 4. I don't know. Giovanni in the chat asked a question, how can we see that the Fokker-Planck Hamiltonian and its Hermitian partner have the same spectrum? Well, remember, just to be specific, this is the Fokker-Planck Hamiltonian, and this, well, I can put a negative here. This is a Hermitian formulation. And let me now remind you how we went from one to another. Well, one way to do that is to start, well, you can do this in different ways. We arrived to the usefulness of introducing the Hermitian formulation by writing the conditional probability as a couple of Boltzmann terms times a quantum propagator. And then we knew the solution of we knew that this was the solution of Schrödinger equation. So use that to reconstruct the equation obeyed by this. An equivalent way of saying the same thing, essentially, is that of starting from the Fokker-Planck equation, which we now give for granted. Let's perform the substitution, or the ansatz, as you want. And then if you do this, you plug it into your equation, you get the Schrödinger equation for your wave function psi. Now, suppose now we have an eigenstate of this function, right? So we have a function phi n such that h effective on phi n is equal to lambda n phi n. Well, question is it also a right eigenstate? Can I use this solution to build a right eigenstate of the Fokker-Planck equation? And what is the corresponding eigenvalue? Well, let me build the right eigenstate of x to be e to the negative b half u of x phi n, for obvious reasons, right? Now, to obtain this, what I do, I multiply the above equation by this. Now, if you do that, on the right-hand side, you have reconstructed lambda n right n of x. Now we are left with dealing with the left-hand side. So the way we do is to perform this non-unitary transformation by doing this. Okay, so now here again we have reconstructed the right eigenvalue. Now it is interesting to see that here we have a complicated rotation on the operator. But if you spell it out explicitly, you discover that this is exactly the calculation that allows you to show that when you take a Fokker-Planck equation and plug in this non-unitary phase transformation to get psi, then you get a Schrödinger equation. In other words, when you act on the derivative on this, and I recommend you to do that, I don't want to do it online, that's 1 gigabyte of quite trivial calculation. If you cannot do that, if you try to group in people virtually, of course, not physically, and try to discuss a calculation, or send me your notes and where you're stuck. But when you apply a double derivative here and you add up the potential on this guy and then you multiply everything by this, what comes out here is exactly the Fokker-Planck operator. So in the end of the day, what you show is that the HF Fokker-Planck operator acting on Rn is equal to lambda n Rn, which means that you have found the spectrum of the Fokker-Planck operator, discovering that the eigenstates are trivially related by a non-unitary transformation, and the eigenfunctions are in fact, and the eigenfrequencies are in fact the same. Okay, I think that should answer your question, hopefully. Let me know if that's convincing.